Okay, let's dive right into this. Welcome back to The Explainer. Today we're tackling the four foundational modes of control: on-off, modulating, open loop, and closed loop. Let's get started.
Think about your home AC for a second. It cycles on, blasts cold air, shuts off, drifts warm, and then cycles all over again, literally forever. It creates this jagged, sawtooth trend. Now, compare that to an industrial distillation column reboiler. It never does that. It maintains a perfectly flat, stable trend. Here's the kicker. They are dealing with the exact same physics, but the control philosophy is completely different. Pick the wrong one, and you'll either cook your equipment or overpay massively for precision nobody actually needed.
So we have four fundamental control philosophies for relating a controller's output to your process: on-off, modulating, open loop, and closed loop. Every single time you design a loop, you are making a deliberate trade-off between simplicity, cost, and precision. Not every process needs tight continuous control, and more importantly, not every process can afford it.
Let's start with the oldest trick in the book, on-off control. It's a discontinuous action, meaning it switches fully on when you're below the set point and fully off when you're above it. As a result, the process variable is going to continually cycle and oscillate around your target. Yeah, it's a bit crude, but it's cheap and it's highly effective for things like a domestic water heater where a bit of temperature fluctuation is totally fine.
And this brilliantly illustrates the core mechanical difference. On-off control? Well, that's just your standard light switch. It's a strictly binary state, fully on or fully off. Modulating control, on the other hand, is a dimmer dial. Instead of that hard, sudden snap, you get a smooth, continuous adjustment. With modulating control, the output moves smoothly through a whole range of values, always staying within defined limits. By completely avoiding those hard mechanical jumps, modulating control gives you a much smoother action. It's constantly making these tiny, micro adjustments just to hold a perfectly steady state.
To really visualize the impact on the hardware, think about driving a car. On-off control is like driving using only full throttle or full brake. I mean, sure, you'll get there, but everyone in the car feels every single lurch, and your brakes are going to be absolutely destroyed. Modulating control applies that smooth, steady pressure to the pedal to maintain a perfect, comfortable cruising speed.
Okay, let's shift gears and look at how this builds into loop architectures, starting with open loop control. In an open loop, the controller applies a completely blind action. The output signal is simply not a function of the process variable. Because there is absolutely zero feedback coming back from the process, an open loop cannot self-correct when conditions drift. It blindly executes its preset command, making it incredibly vulnerable to unexpected process disturbances.
A perfect everyday example is a standard washing machine. It operates in an open loop because it blindly runs its wash, rinse, and spin cycles based entirely on a preset timer. It never actually measures the end goal, which is, the cleanliness of your clothes. If you toss in a load of incredibly muddy gear, it runs the exact same time cycle as it would for lightly worn shirts. It has no feedback mechanism to know if the job was actually done right.
Now, what's really interesting here is this continuous feedback architecture. Closed-loop control or feedback control is the absolute foundation for every PID loop in the industry. It takes the actual process variable, continuously measures it, and compares it to your set point to calculate an error. Then it dynamically updates the control action to eliminate that error, constantly self-correcting against unknown disturbances.
All right, quick check for you. Let's put this into practice. Imagine you are the engineer tasked with designing a control system for a simple parts washing tank heater. The only real requirement is that the water needs to stay warm enough to dissolve grease. So, would an expensive, closed-loop modulating control system make sense here? Take a second and really think about it.
Actually, the answer is a definitive no. Putting a full modulating loop on a simple tank heater would be totally wasted money. The tolerance here is incredibly wide, and a giant tank of water is a very slow-moving process. That wide tolerance perfectly suits simple, cheap on-off control. But let's flip this scenario entirely. What if you're controlling a fast, dynamic offshore gas compressor? This isn't a slow tank of warm water. We're talking about highly volatile equipment where pressure ratios change in literal milliseconds. Here, closed-loop modulating control is absolutely required. An anti-surge valve has to continuously creep and adjust, reading flow and pressure to stay off the surge line. A wide tolerance or a lurching on-off action here wouldn't just be inefficient, it would be utterly catastrophic.
So, the crucial point is that every control choice is a trade-off between your budget and your process demands.
On-off is simple and cheap, but you lose precision and introduce high mechanical wear. Modulating in closed-loop systems, they give you that high precision and low wear, but you sacrifice simplicity and have to pay a much higher upfront cost for intelligent sensors and positioning valves.
I really want to leave you with this stark warning before we wrap up. Picking the wrong mode isn't just an academic mistake. It actively destroys equipment. If you use on-off control on a mechanical valve with tight cycling limits, the rapid chattering, switching violently between full open and full closed, creates severe mechanical stress. If a loop is chattering rapidly, it is quite literally tearing itself apart. You're basically trading a slight upfront cost saving for a massive, expensive maintenance failure down the line.
So, we've nailed down the baseline philosophies of how controllers interact with processes. But what happens when these systems are pushed to their absolute limits? Next up, in Part 2, we'll break down that compressor surge example where getting this wrong is a literal disaster. Ask yourself, what exactly happens when an open-loop system is suddenly hit with a deadly, unforeseen disturbance? Stick around to find out.